Oh, hi. I didn't even see you there. What's that? You want to hear a chemistry joke? Okay. What do you do with a dead chemist? You bury him. No? Oh. You want to learn about VSEPR models and Lewis structures? Okay, let me call up my friends.
Hey guys, I'm Sahar. Hi, I'm Rashika.
And I'm Hannah. We're going to be teaching you about VSEPR models and Lewis structures. I would strongly suggest that whenever you hear this noise, pause your video and write down whatever is on that slide so you can remember this important information. So let's practice now. Pause your video and write down how to construct a Lewis structure. For the atoms in the s and p orbitals, just look to their group number. Take the number in the ones place, and that's how many valence electrons there are. See? It's easy. Hey guys, I'm going to explain how to make a Lewis structure for carbon dioxide or CO2. First, we're going to count the number of valence electrons for each atom and then add them up. If we count the valence electrons, we will find that CO2 has 16 valence electrons. Now we're going to draw out each atom and put the carbon atom in the middle of the two oxygen atoms and draw bonds to connect them. Each bond counts as 2 valence electrons. Once we've done this, we can complete the octets for each atom, drawing pairs of electrons so that there are 8 on each atom. When we do this, we will find that they don't add up to 16, so we are able to create double bonds between both oxygen atoms and the carbon to complete carbon's octet.
This is the carbonate ion. Let's begin drawing the Lewis structure for this molecule.
But first, take a second to look at the charge of -2 on this carbonate ion. This charge indicates that there are 2 more electrons than protons in this molecule, and thus we must add these 2 electrons to the total number of valence electrons.
So, you may notice that there are 3 different ways to place the double bond in the structure. This type of ion requires resonance structures. These structures are used because all 3 resonance forms exist simultaneously, and the strength of all 3 bonds are the same. One example of an electron-deficient species is BeH2. The valence shell of Be is capable of containing only 2 electron pairs. Another example of an electron-deficient species is BF3, more commonly known as boron trifluoride. The valence shell of boron is capable of containing only 3 electron pairs. Examples of atoms capable of containing more than an octet of electrons are depicted in these 2 molecules, phosphorus pentafluoride and sulfur hexafluoride. Both the phosphorus and sulfur atoms are located in the 3rd period, and thus they are able to have more than an octet of electrons. This can only occur if the valence shell has enough orbitals to accommodate the extra electrons. Hydrogen is an atom which has only 1 electron pair. Halogens, located in the 7th group of the periodic table, are atoms that are only capable of having 1 electron pair. On to VSEPR models. These models will be coming in super helpful for both this class and the AP Chem test. We're going to be explaining how to do electron domain geometry and molecular domain geometry.
Basically, the electron domain geometry models are the basic shapes of a molecule with no lone electron pairs. The molecular domain geometry models are the shapes of molecules with lone electron pairs, which repel the bonding pairs.
The electron domain geometry models will be illustrated with candy models. The molecular domain geometry models will be illustrated with on-screen notes. So, whenever you hear this noise, make sure to pause the lecture and take notes. Oh, and one more thing. The hybridization of these molecules explain the shape the molecule takes with a certain number of electron pairs.
Wait, we forgot to mention angle measures. The angle measures measure the repulsion between the electron pairs.
Have we covered everything? Yep, I think you guys are set. Let's go look at some VSEPR.
Models.
This is BeCl2. Its electron domain geometry is linear. That means it has an sp hybridization and angle measures of 180 degrees.
This is BF3. Its electron domain geometry is trigonal planar. That means it has an sp2 hybridization and an angle measure of 120 degrees.
This is CH4. Its electron domain geometry is tetrahedral. That means it has an sp3 hybridization and angle measures of 109.5 degrees.
This is PCl5. Its electron domain geometry is trigonal bipyramidal, which means it has angle measures of 90 degrees on its axis and 120 degrees around its equator. Don't worry about hybridization for trigonal bipyramidal molecules. Scientists haven't quite figured it out yet.
This is SF6. Its electron domain geometry is octahedral and has angle measures of 90 degrees. Again, don't worry about hybridization for octahedral molecules.
Let's revise everything we've learned today. In summary, thanks for watching.
Now you're experts. That was pretty good.